Hello everyone, today let's solve the problem number 105. Construct binary tree from preorder and inorder traversal, right? So what the question states here, so we have been given two integer arrays, one is preorder and another one is inorder. You can clearly see we have been given two integer arrays, one is preorder, yeah, and one is inorder. You can clearly see here, right? So what we need to do then, so we have to construct and return the binary tree, final binary tree. So they have asked we have to construct and return the binary tree. We have been given preorder and inorder integer arrays, so we have to construct and return the binary tree. So that's what they have asked. So let me tell you one thing first. So preorder, so the order, when I say preorder, the order starts from root, then left and right, right? So this is the order basically when I speak of preorder. So you should be knowing this one: root, left and basically right. Just give RT, right? So what is in order then? In order basically starts with left first, then root, then right, and left, root and then right. So just keep this in mind, right? So this is preorder and inorder traversal. So when we traverse, when someone says, or when we traverse through the preorder, so it is nothing but when someone says preorder traversal, that means we are considering root first, then left a subtree, then right subtree, right? So when someone says inorder traversal, or when we are traversing through the inorder, or if someone says inorder traversal, then first we will consider the left subtree, then root, then followed by the right subtree. Just keep this in mind. This is important, right? So here in this case, what they have asked us to do, they have asked us to construct and return the final binary tree, right? Here in this case we have been given this one, preorder 3, 9, 20, 15 and 7, right? So this one is considered null basically. Here you can clearly see this is considered null. We have to consider null if we do not have children for the particular node and we have the particular level, right? So we have the particular level here. In this case, children are present for the 20. If children are not present for the 9, then we have to consider null. Just keep this in mind. So this is fine. Now we have 3, 9, 20, 15, 7. This is pre-order, right? So 3, 9, 20, 15, 7. Root, left, right. Then again, this one we have already considered 3, 9, 20. So left, right. This is fine. So in order, left, this one and this one, right? 9, 3, 20. So 9, 3, yeah, 15 we have to get, right? So we have the children for this. 9, 3, 15, then 20 followed by 7, right? So don't get confused. Yeah, 9, 3, this is having the children. So 15, left subtree we are considering first. For this one we are considering root 20 and again 7. This is fine. This is the in order. So what would be the normal binary tree here? So first we have to go with 3, 9, 20. This is fine. Null, I have said if we are having the particular level and we are not having the children for the particular number, then we have to consider null. I have said this one earlier, right? So we will be considering two null values here, null, 15 and 7. So 3, 9, 20, null, 15 and 7. This is fine. So this is what we are going with. So this is what we need to return, sorry. So in the form of output here, you can clearly see here. The output is 3, 9, 20, null, 15, 7. This is fine. So just give me a second here. So yeah, let's come to the second example. So we have been given only preorder 1 and inorder 1. In this case, the output will be quite obviously -1 itself. Means -1, we have only one element, right? So in this case, we will return the same element, right? So we will return same element as the binary tree. This is fine. I hope this is completely clear. So they have given wonderful examples for just for the sake of understanding purpose. Here now we are now I hope the question is completely clear. What we need to do is completely clear as well, right? So let me clean up this one. So first let's discuss the approach, then followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, as usual, let's discuss the approach first. So the first thing that we need to keep in mind here is we will be going with the recursive and divide and conquer using hash map. This is the approach that we will be going with. Recursion, basically recursive divide and conquer method along with the hash map, right? So this is the method that we'll be going with. Now we have solved many problems using the recursion. We also know divide and conquer method as well. So first itself we have solved the hash map problems as well. So total, so here in this case the approach that we'll be making use of is recursive divide and conquer using the hash map, right? So I have considered the first example, the same example that they have given in the question, so that it will be easier to understand. We have already discussed this one, 3 9 20 15 7. We're looking at the diagram. We have to get the output 3 9 20 null null 15 7. If a particular node, if the left or the right subtree both are present, and if the right subtree or the left subtree is having this one, the values, and but if suppose if the left subtree is having the children and the right subtree is not having the children, then in this case, and then in that case we have to consider null values. Just keep this in mind, right? So let's go with the step-by-step execution. So the same first example we are considering right here. So first step here is we have to pick the root. So we have to pick the root in this case. So the first element of pre-order here, we are going with the pre-order. The first element in the pre-order is always the root. We know this one, right? Pre-order, order of the elements, order of the execution is left, root, left, and then right. So this is for the pre-order. I'll just give pivot here. So for the in order, it is left followed by the root and then right. So we know this one, right? We have solved n number of problems already. So this is fine. This is for the pre-order and this is for the in order, right? Just keep this in mind. The first element of the pre-order, it has to always start with the root, right? Root is 3. We know that one. From the example, root is 3. So this is the root basically. Let's move on with the second step. We have to find the root in the in order as well, right? So we have to find 3. We already have the root 3 for the pre-order, right? So we have to find 3 in the in order, which splits into basically left subtree and the right subtree, right? So we are talking about the in order here. We are speaking of in order here. So we have to find 3 in order, which splits into basically left and right subtree, right? So in order left part here is 9. I'm speaking of this one. In order left part is 9, which is basically the left subtree of this one, pre-order, right? So in order left part is 9. The right subtree here in this case, in order right part is 15 27. So in order I'm speaking of. So when we considered the right part, first we considered 15, then the root, right? In order we are speaking of left, root, then right, right? 15 we considered, then followed by 20 and then 7. During the example, I explained the same thing, right? So I explained the order of the traversal for both pre-order and in order, and we saw both how it works, right? So for in order it was 15 20 and then 7, right? So in order right part, so this one 15 27, this is fine. Now we know this one, right? So let's move on with the third, right? Let's move on with the third step or the final step here. So left subtree. So now we have the pre-order element 9. That basically becomes root. Now we have already considered root. Now we have to consider the left subtree here for the pre-order. So 9 becomes root now, right? 9 becomes root. Here you can clearly see me. I didn't draw a tree. Just give me a second here. Let me draw this one so that it will be easier to understand. 3 9 20, so 15 7 we have. So we have already considered 3, right? So we have already considered 3 as root. Now we will be considering this one, basically 9 as root. Now 9 will be root, quite obviously, right? Let's come to this step in this case. So pre-order element 9 becomes root. So this is not having right or the left children, since in order has only 9, right? So here you can clearly see this is not having any children here, right? This is not having any children here. So since in order is only 9, what we will do, we will move on to the right subtree. So we will move on to the right subtree. This is second part, right? Next pre-order element 20 is the new root here in this case. Next pre-order element 20 is the new root here. So 20 will be the new root here in this case, right? So this doesn't have children, so we have to consider 20 as the new root. We have already considered 3, so this doesn't have children, so we will be considering 20 as the new root here in this case, right? Let's come to this part. So we are done with this one, right? So left of 20 is 15 and right of 20 is 7. Pre-order I'm speaking of. So let me come here. So left subtree of this one 20 is 15 and right subtree of this one is 7, right? So this is fine, we know this one. So let's come to the this part. Final tree structure as put 3 9 20 null 15 7. So here this is having the this root is having 15 and 7, means this level is having the children. Basically 20 is having the children, right? This third level we are having. So when we are having two roots 9 and 20, and in this case we are having the children, right? 9 is not having the children at the third level, so we will return null for this one. So I have said this one several times, right? So the output will be in this case 3 9 20 null 15 7, right? So this is same as, or this is equivalent to the output that they have given for the first question here in this case 3 9 20 null 15 7, right? So this is equivalent to the output that we got is equivalent to the output that they have given for the first example, right? First example. So this is the approach that we will be going with. Approach works absolutely correct, right? So this is the approach that we'll be going with. Now, as we are familiar with the approach, let's discuss the edge cases quickly. So the first edge case is for this one, single node tree here. In this case, pre-order is -1, in-order is -1, output will be -1 as well. We have already discussed this one, right? So a tree with only one node results in itself as output. Just keep this in mind. We have already discussed this one in the example itself they have given, right, in the question. So let's go with the second edge case, left skewed tree. We'll be considering for left and right skewed tree. Basically, let's discuss left skewed tree here in this case, right? So pre-order is 5 4 3 2 1. Post order is in order is 1 2 3 4 5. We know this one, right? This is completely left skewed tree. This is completely left skewed tree. We will get on this way 5 4 3 2 1, right? So now what we will do in this case, we have the left subtree. So for this one we will be going with null, this one will be going with null, this one we will be going with null, and for this one also will be going with null. It will be 5 4 null, 3 null, 2 null, and 1. So we'll not be going with this one, right? So this is fine. Sorry, 3 null and finally 1. This is the output that we'll be getting. So this is right skewed tree. In this case, we will be having 1 2 3 4 5. So we at this level we have null, right? So we have 2, so we'll be going with null. This one also null. Finally, this will be 1 null 2 null 3 null 4 as well as this one null 5 in this case, right? So this one has to be 1 null 1 we have given right here in this case. This is fine. This is the final one, right? So we don't have to give null here. This is fine. So in this case, 1 null 2 null 3 null 4 null and 5 is the output that we get here for the proper binary tree. So let's move on with the final edge case here, balanced tree. We have the pre-order 2 1 3, in order 1 2 3, output will be 2 1 3 itself. So we have 2 1 3. So the proper binary tree will be 2 1 3 itself. In order starts from left, this one, root and right? So for the pre-order it is root left and right, 2 1 3. For the in order it is 1 2 3. So output will be quite obviously 2 1 3 itself, and we do not have children for 3 or 1, so we'll stop it here itself. The output will be 2 1 3. This is fine. These are the 4 edge cases that we need to keep in mind. So the first edge case is for the single node tree, the second edge case is for the left skewed tree, the third edge case is for the right skewed tree, and the final edge case is for the balanced tree. So these are the edge cases that we need to consider here, right? So now we are completely familiar with the approach as well as the edge cases. As we are familiar with the approach and edge cases, it will be easier for us to write the code. Let's start writing the code. So first step here is we have to store the index of each value in the in order array for big of 1 lookup. So we are making use of the hash map, right? So basically it is divide and conquer, recursive divide and conquer using hash map. So we are storing index of each value in the in-order array for just big of 1 lookup. So let me quickly write here. Let me come here. Just give me a second. So let me give here in this case. So this one private. So we are going with the hash map. So I'll just give here map integer comma integer. This is fine. So I'll just go with in order index map. This is fine. Again, I'm telling why we have written this. Basically, we are storing the index of each value in the in order array for the big of 1 lookup, right? So also we have to track the current index in the pre-order array. So for that one, I'll be making use of the pre-order index. So just give me a second. What happened to this one? So I'll just give here private int pre-order index. Let me initialize this one to the 0. This is fine. So next step here is let's come to the main function here, build tree. What they have given build tree right here. Within this one, let's initialize the map first. I'll just go with in order index map. We are making use of hash map, right? So I'll just give here new hash map. This is fine. So after initializing the map, let's traverse through the array. Let's traverse through the array, and we have to store the index of each element from the in order array, right? So let's go with the iteration first. It will be int I equals 0, I less than in order dot length. So let's increment the I here. This is fine. So let's store the index of each element from in order array. So what shall I give here? In this case, in order index map dot put here. In this case, I'll just give in order of I comma I. This is fine. So after this step, or after storing the index of each element from the in order array, so what we will do, we have to recursively build the tree. For recursively building the tree, I'll be making use of the helper function construct tree, right? So before writing this one, let's make use of the helper function construct tree. This will basically help us for recursively building the tree. So I'll just give here in this case private tree node construct tree. This is fine. So within this one, I pass the parameters here. This one pre-order as well as left and right. So I'll just go with pre-order left and right. This is fine. So the first step within the construct tree function here is base case, right? We have to return null when range is invalid. When the range is invalid or out of bounds, we have to return null in this case. So I'll just give here left greater than right. It shouldn't be because it is BST. So we will go with this one in this case. What do you call? We have to return null in that case. So this is fine. So the next step here is we have to pick the root from pre-order, because pre-order always starts with the root, right? So that is the reason we have to pick the root from pre-order. So I'll just give here root, or let me give root value here on this case. Root value. So I'll just give here pre-order of pre-order index. We have to increment the pre-order index. I'll just give here pre-order plus plus. This is fine. We are just picking the root from the pre-order, and we have to create the root node. So I'll just go with here root. This one new tree node of we have to pick the root node, right? So I'll just give here root value. Let me pass the root value here. This is fine. So the next step, we have to find the root position and in order. So this one will be int in order index here. This is fine. This one in order index map. So I'll just make use of the get property to get the value, right? To get the basically root value. So I hope this is clear, easy to understand, right? So the next step, we have to construct the left subtree as well as the right subtree. After the root, we have to construct the, quite obviously we have to construct the left and right subtree, right? So for that one, I'll just give here root dot left, and here let me make use of the construct tree, this one, construct tree of first preorder, here in this case left and right. So this is the basically order, right? So preorder left and right, root left and right. So in this case it will be preorder in order index plus 1 and right, because in the case of right, so when I give root dot right, so because it is in order, right? So I'll just give here root dot right equals, so let me copy, I should have copied the entire line and made the necessary changes. So this is fine. So in this case I'll give the same thing. First it will be preorder itself, the second one will be, we are dealing with the in order, right? So this will be in order index plus 1 in this case, and finally this will be right itself, right? So this will be basically left and in order index minus 1, it has to be, right? We are going with the in order index plus 1 for the right. For the left we have to go with in order index minus 1. So this one, sorry, I got confused here, these two. This is fine. This is fine. Finally, we have to return the constructed subtree. So when I say we have to return the constructed subtree, means we just have to return root in this case. So this is fine. So this is it for the construct tree function. Next, I said we'll be recursively building the tree. Let's make use of the construct tree function here. So I'll just copy this one. So here in this case, let me come here. Let me give return construct tree of preorder 0 and inorder this one, length of the inorder minus 1. So we are just recursively building the tree. So this is fine. Let me format the document once and let me hit the run button. So here we are having root value. So this v has to be capital, I think. Error cannot find value. Line number 20. So this one root value, we have kept the v capital here on this case. So this has to be v. V has to be capital. Let me hit the run button again. Yeah, now you can clearly see the sample test cases are getting passed, right? So let me hit the submit button quickly. So I hope this works for all the test cases. Let's see. So yeah, now we can clearly see all the test cases are getting passed. Means the code works absolutely correct on this case, right? So now, as it works for all the test cases, let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is recursive divide and conquer using the hash map. We know this one, right? So we have went with recursive divide and conquer using the hash map. So what will be the overall time complexity here? Overall time complexity would be big of n. Why it is big of n here? Because we have processed, or actually we have processed each node exactly once, right? Accordingly with the code I'm of, right? So each node is processed exactly once, and then in order lookup is big of 1, because we are making use of the hash map. Here you can clearly see the first step itself I had explained the same thing, right? So here each node is processed exactly once, and in order lookup is big of 1 using the hash map. So overall time complexity would be quite obviously big of n, right? So what would be this overall space complexity here? Overall space complexity is big of n as well. Why? Because we are making use of the hash map, means due to the hash map storage itself, right? And also we are making use of the recursive call stack. So in the worst case, I mean, always when I say worst case, every time we discuss this one, in the edge cases we discuss left skew tree and the right skew tree for in the edge cases, right? Always for every problem I have considered left and right skew tree, right? So when I say left and right skewed tree, it is the worst case that we are considering in the edge cases, right? So it is for the worst case. So we are making use of the hash map, nothing but hash map storage and also recursive call stack in the worst case for the skewed tree. Either it may be left skewed or whether it may be right skewed. It is big of n. We know that, right? In the worst case, recursive call stack depth in the worst case for the skewed tree is big of n. For both hash map storage as well as the recursive call stack in the worst case for the skewed tree is big of n itself. So we are considering overall space complexity as big of n. So the time complexity is big of n and the space complexity is also big of n for the code that we have written. I hope the complexities are completely clear, and I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.